Okay, so we are in Causal Inference and Statistics, that book right there. We're in Chapter 3, and we're on question 3.4.1. Okay, so here we revisit this DAG here, and we want to estimate the causal effect of x on y, but we're only allowed to measure one additional variable. Okay, and so here we're supposed to say what variable that would be and what the expression would be. The expression, the mathematical expression for the causal effect of x on y. Okay, so first let's think our way through this here. There are some. To this point, we've been using the backdoor criteria and adjustment almost exclusively, and so here we see that there are some backdoors from x to y. There is x, a, b, z, so on and so forth. Okay, and so we might condition on a or b, and that would close down that pathway, or z. Okay, but there's also this backdoor path that goes from x to z to y. All right, and so we can't. We would have to condition on more than one of these backdoor variables here in order to close them all down. Okay, so because we're only allowed to do one, we probably can't close down the backdoor paths, just given the constraints of this particular problem. But we do recognize that, well, if we've read up to this point in the chapter, we recognize this structure that goes z, x, w, y. All right. And we can use this structure to utilize what's called the front door adjustment, okay, because it meets the front door criteria. Okay, what does that mean? All right, so what we're going to do is, instead of conditioning on any of these backdoors here, we're going to bypass the whole backdoor problem and just estimate the effect of x on y by accounting for the effect of x on w and the effect of w on y. Okay, so let's talk about it. So that's called the front door adjustment. Okay, so how do we apply the front door adjustment? Well, first we have to identify a set of variables that meets the front door criteria, and here that set of variables is going to be one variable. It's going to be w. So what is the front door criteria? All right, so applying it to our problem, it has to be that that there is a set of variables, here it's just w, that w intercepts all of the direct paths from x to y, right? And there's only one direct path from x to y, and it goes through w, so the first criteria is met. That there are no unblocked paths from x to y, okay? So there's the direct path from x to y, all right? So that's fine. We want to keep that one, but there's other paths, right? Basically these backdoor paths. But in order for those backdoor paths to for us to get to x to y via the back door, we ultimately have to go through y, but we're conditioning on y. So all of those backdoors are closed there. Okay. And then all paths from w to y are blocked by or all backdoor paths from w to y are blocked by x, right? So there is a backdoor path that goes from w to y, but it all goes through x here. Okay, so that path is blocked. Right? So w meets our criteria for the set of variables that would allow for the front door adjustment. Okay, so the front door adjustment is well, what are we going to do? Well, we need to account for the effect of x on w and then the effect of w on y, and we're going to do that by applying the backdoor adjustment for both of these legs in our little journey from x to y. All right. So we're going to have to find w do x and then y do w. All right. So let's break those down. So the first one we want is the probability of y do x. Okay. So I'm just going to apply the backdoor adjustment here. Okay. But there are no open backdoor paths here. Okay. They're all being blocked. So our backdoor's terms here, they all drop out, And so we just get the observation of probability of y on x. Okay, so that's the first leg of our journey from x to w. Okay, and now we want to estimate the effect of w on y. Okay, this right here. All right. This again is the backdoor adjustment. So we're going to apply the backdoor adjustment here, and again now there's a backdoor from w to x. Okay, and so we get this expression for probability of y due w. Okay, and so now we just need to string these together, right? So we have a due expression for this leg and then for this leg, and so we need to string them together. Okay, so we're just going to put this one in front of this one, with one added little complexity here, which is that we want to account for all values of w here, right? Because if x is whatever value it is, it will probabilistically determine the value of w. In other words, any value of x could lead to different values of w in a probabilistic manner, right? So some, for any value of x, some values of w are going to be more and less likely. Okay, so we want to account for all values of w. So what do? Well, we just sum over all values of w here, right? So we take our first due expression, plot it here, or plug it in here. Then our second expression, we plug it in after that. And then because we want to account for all values of w, we sum over all values of w. Okay, and then you'll notice these little tick marks after the x here. The book does that. It's probably a good idea, but it can be a little bit confusing. But roughly, or I mean, basically, what it's saying is it's separating the x values from this due expression from this due expression here, right? And it ensures that we're only summing over, right? So when we want to know the probability of y due w, that we're only summing over the x prime values, right? Because that's the only place where that summation should be occurring. So anyway, so that is our final expression for the front door adjustment that gives us the effective probability of y due x.